Hi, thank you for joining us today. So in the last 5 years, the loss of pollinator habitat, long-term decline in beekeeper numbers, and waning bee health and historically low numbers of bee colonies in the United States has created widespread public concern over the future of our food supply. Upon realizing that 2 of every 3 bites of food requires pollination, industry, interest groups, and everyday citizens have new interest in honeybees and wild pollinators. This has translated to increased pressure for lawmakers, the president, and other government agencies to take fast action to produce policy. In the rush to save the bees, numerous threats have been listed as top policy priorities. They include pesticides, pests and diseases, climate change, bee transportation for migratory beekeeping, and habitat fragmentation. Perhaps the one threat that is most divisive and has also received the most public and industry attention is neonicotinoid pesticides. This spotlight has intensified as other countries, including the EU and Canada, have placed bans on this class of pesticides. Today, I would like to take the time to shine the spotlight in another direction. According to a survey of the literature on research into pollinator health challenges, land use change and resulting habitat fragmentation actually rise to the top of the list as the most detrimental to managed and wild pollinator health. Important steps can be made to achieve this goal by integrating ecological science and research with economic tools and policy analysis. On slide 3, I illustrate the relationships among economic and ecological systems affecting pollinator health. On the right-hand side of the infinity diagram, we see pollinator abundance and productivity is a function of their habitat, surrounding biodiversity, and ecosystem functioning. All of these factors rely on general landscape characteristics, including the availability and proximity of land for pollinator habitat. Economic relationships affecting pollinator use and health are illustrated on the left-hand side of the infinity diagram. It is within the economic dimension that we see how pollinators influence and are influenced by human behavior. Their contribution to agricultural production may be directly measured through crop yield improvements. Higher crop yields then affect both the relative price of the crop in the marketplace and the land it was produced on. Crop prices, of course, are not just a function of crop yields, but also consumer tastes and preferences for the commodities. Pollinated crops tend to be higher value crops. In theory, pollination increases crop supply to the commodity markets, leading to decreased food prices and increased consumer welfare via those lower prices. Pollination also appears to increase the quality of fresh produce. A recent study published in the Proceedings of the Royal Study by Klatt and his colleagues show pollinated strawberries have a longer shelf life and fewer imperfections, resulting in more value at the supermarket. The resulting crop and retail prices affect consumer and producer welfare. This informs producer decisions for the next round of production, guiding not just their crop choice, but the agricultural production practices, crop varietal, and chemical input choices they make. These decisions then directly influence the surrounding ecological system, creating a never-ending cycle of relationships. From this illustration, we can see analyzing ecological influences on pollinator health alone overlooks the importance of human activity on their well-being. No place is this more obvious than for managed honeybees kept by beekeepers. They depend directly on both systems and contribute to targeted crops through human transportation. We can look at Conservation Reserve Program data from 2007 to 2012, and I just realized my screen has this in it. Excuse me. 2012 to get a sense of how the landscape is changing in different areas of the country. So going back to that figure, you can see where areas that have orange and red colors have lost a lot of CRP acreage over the last 5 years preceding 2012. The size of the green dot indicates how much of that acreage was converted to agricultural farm use, cropland use. The larger and darker the green dot, the more transformation of the landscape went to agricultural uses. The northern Great Plains and Intermountain West serve as important summer feeding ground for managed honeybees on break from pollinating along the west coast. This is also an area of the country that has seen the greatest changes in land development and conversion of conservation land to cropland. If farmers were converting their land to pollinator-friendly crops such as sunflowers, clover, and canola, this wouldn't be a substantial threat to pollinators. However, in many areas, farmers have shifted to less pollinator-friendly crops such as corn and wheat. It is not just the number of fields that are growing, but also the individual field size is growing as well. As land moves into production, it is often converted by the quarter section, not just 40 to 80 acre parcels. These quarter sections can quickly add up to miles of cropland with little or no pollinator habitat. In this stylized representation of a farm landscape, imagine this is a 2 by 2 mile square divided into quarter sections, 6 by 6 miles divided into quarter sections. You can imagine that as if those quarter sections then become larger land strips, the CRP land, which is represented in the brown color, may decline as that land is converted into agricultural production. Also, not only is the land converted into agricultural production instead of being in CRP, there's fewer field margins between fields, so there's less area for pollinator habitat among crops. For bumblebees whose habitats are typically rather small, or approximately 50 to 100 meters, this is devastating. For honeybees who forage over much larger areas, reduced habitat means moving or traveling farther for life's basics. Instead of foraging within a 3-mile radius, they may be forced to forage 6 to 10 miles from their hive. This increase in foraging distance is likely to cause stress and fatigue to bee colonies. Survival may not be an option if there aren't floral and water resources within flying distance. As we consider agricultural landscape policies, lawmakers have considerable challenges to balance agricultural production and ecosystem needs to support pollinators and people. When dealing in the fog of war, so to speak, it can be difficult to determine which policy is best to pursue, especially with existing scientific uncertainty around pollinators, especially wild pollinators. A survey of the ecological literature suggests a number of in-field and beside-the-field practices that can be used to combat the effects of habitat fragmentation. Pollinator health is improved when synthetic pesticide use is reduced. It can also be improved if chemical applications are made at night or during pollinator inactivity to reduce their exposure. Pollinator health improves with reduced tillage and drip irrigation that cause less disturbance for ground-dwelling pollinators. Pollinators' food supply can be supplemented through planting flowers within non-agricultural crops. Practicing organic farming techniques is also considered more pollinator-friendly. One of the greatest ways to enhance pollinator habitat is by sowing flowering crops such as sunflowers and clover. However, it's important to try to provide a mix of crops that flower across the season so pollinators have continuous food supplies throughout the spring, summer, and fall. Beside the field, there's also additional actions that can be taken. These include providing nesting resources for bumblebees and other native pollinators, which can include planting more hedgerows and flowering strips throughout the fields and along the sides of the fields, conserving natural and semi-natural areas so that they provide more habitat, and decreasing the size of fields so there's more margins between fields for habitat to develop. This also relates to increasing the diversity of crops across the landscape, moving more from monoculture landscapes to landscapes with a variety of crops across the landscape. These options are comprehensive in scope, especially when you're looking at the landscape level. They are also achievable in most regions of the country. Still, if they were given equal weight as policy recommendations, producers and land managers would likely embrace some and reject others over time. Their adoption would likely rely on government regulation and compensation. Today, I want to emphasize the role economics can play in policy development and decision processes. I know the House Agricultural Committee members are very concerned about the trade-offs around pollinator conservation and food production. We can clarify policy directions with economics using economic tools to estimate the economic costs and benefits of landscape design policy for pollinator habitat. The key policy question is to identify which options are economically feasible. So let's discuss some of the economic approaches, tools, and findings that may inform pollinator policy. First on the list is the tried and true supply and demand analysis. Over the last 30 years, the U.S. beekeeping industry has shifted from primarily producing honey to pollination servicing. As this has happened, a market for pollination servicing has developed. These changes have also caused changes within the industry structure of the beekeeping business, with many small firms exiting the industry and larger firms achieving economies of scale, especially for migratory beekeeping. The evolution of managed pollination services market provides a starting point for the economists to evaluate the value of pollination in agriculture. Using supply and demand analysis, we can use the market price for pollination services as one indicator of pollinators' value in agricultural production. Obtaining such a value will help us understand how much public and industry money should be invested into conservation efforts to support their health. Recent work by Rucker, Thurman, and Burgett from 2012, published in the American Journal of Agricultural Economics, demonstrates knowledge of the market for pollination service and the value of managed honeybees in pollination is still being curated. They developed this figure to illustrate the market changes in pollination servicing over time. As you can tell, in the mid-1900s, there was very little use of managed pollinators in almond production in California. Over time, this has risen to the point where regional and local honeybees can't meet the demand for pollination services in that area. This has created a regional and nationwide market for pollination services. I present a simple supply and demand diagram for pollination services in slide 9. This model provides one basic economic approach to understanding pollination value. The pollination value for different crops can be reflected by the contract price for bees for those crops. In this figure, the orange line rising to the right is the supply curve, and it represents the cost of supplying pollination services to growers. And the blue line is the grower demand curve for pollination services. If we are able to identify the supply and demand curves, we can then estimate the value of pollination to crops, in this case, almonds in California. So suppose in 2015, the almond contract price was about $190, and the number of colonies demanded was $1.6 million. The total value for honeybees across the almond crop was $304 million in production alone. While this is an intuitive and nice approach, there's still a lot of research to go to understanding the true supply and demand of pollination services. We can use these rough estimates, but to really do forecasting and move the analysis into the future, we need to understand the drivers of both the supply chain and the supply curve and the demand curve. Right now, my colleagues and I here at the University of Wyoming, Montana State University, and Utah State University are working through funding from USDA to understand what are the drivers of the supply curve and the demand curve for pollination services in the western United States. This will also help us as we think about in the future understanding how natural pollinators may augment the price of pollination. Our original P and Q may actually be something more like P and Q star when we think about how much natural pollinators are augmenting pollination demand so that fewer managed pollinators are needed. Also, some research shows that wild pollinators help to increase the productivity of managed pollinators. So it's important in supply and demand analysis also to understand the ecological interactions between wild and managed pollinators. Another great source of economic insight can come from crop production modeling. Right now, while crop production depends greatly on pollination, there's really a dearth of information available about the production responses of crops to pollinators. Most of the research that has been done on honeybees, and we have very little understanding of wild pollinators' contribution to crop production, especially across a variety of crops. The research that does exist tends to focus on almonds, blueberries, and alfalfa, and watermelons. So in the future, there's great opportunities for information from economists willing to work with ecologists, agronomists, and others on this. Dan Sumner and his team at University of California, Davis is working in this direction with their work on almond pollination. So a missing link in much of the research on pollinators is also understanding their societal value. People value pollinators for more than their agricultural production. They value the fact that they exist. They enjoy looking at honeybees and butterflies and hummingbirds. The monarch butterfly in and of itself it illustrates the case that pollinators add more than production value. People value the phenomenal migration that insect makes and want to help protect it. As we consider how much to invest in pollinator policy, it's important to make sure to get non-market measures of their existence value, their contribution to natural floral and arboreal services, and their contribution to biodiversity in general. Finally, one area that's often overlooked is the importance of understanding how regulatory framework and behavioral responses influence policy success. When we look at the modern agricultural landscape, we see not only a highly fragmented landscape in terms of its physical makeup, it's also highly fragmented in terms of its ownership. There's the Hatfields and McCoys trying to make it work, and we're trying to think of policies that can make them work together to provide habitat in frequent enough intervals so that they benefit pollinators. Part of our work here at the University of Wyoming looks at what kind of group coordinating mechanisms and bonuses would work to bring people together to coordinate habitat, over privately held land parcels across a landscape. So, in conclusion, I have a few recommendations that I'd like to send forth to people working with pollinator policy. First and foremost, we need to be sure to integrate the economic and ecological sides of pollinator issues in our analysis in order to develop policy that will stand the test of time. We also need to make sure to include not just the value of pollinators' contribution to production agriculture, but also their contribution to society in terms of the beauty and biodiversity they bring to our world. Finally, we believe, obviously, because we're economists, that economic tools and analysis can aid policy decisions. There's a rich area of work to be done. Some of the basic things that have been done for other crops and livestock for over a century, such as basic production budgets, are just starting to be done for pollination services, and we're excited to see where this can take policy in the future. For further reading, you can look at our current choices article entitled the same as this presentation, Integrating Ecological and Economic Considerations for Pollinator Habitat Policy. Please feel free to contact me at my UW email. I also want to thank funding from the USDA and University and State of Wyoming for our research, the sponsorship of today's seminar from CFAR and the AAEA, and also all of the colleagues and students who've helped support our research here at the University of Wyoming. And last but not least, thank you, Wyoming Beekeeping Association and the Laramie Bee Cat Group.